4.4 problems in 2 dimensions. So we're working with trigonometry, and you've been so disappointed that we haven't really been talking about lengths and angles and triangles. So we're gonna do some of that. Okay. The first thing that we need to talk about is something called the ambiguous case, and I'd like you to investigate it a little bit and think about it a little bit. Let's say you had a triangle, and you know that one of the lengths is 5. Let's call it 5 centimeters, and let's say that you know one of the lengths is 8 centimeters, and you know the angle. You know that one of the angles, let's call it angle A, is going to be 45 degrees. Go ahead and try to draw the triangle that suits those qualities. All right. If you paused and tried that, good for you. Here's the thing. Since this is actually an ambiguous case, in which what that means is that there's actually 2 possible solutions. So there are 2 possible triangles that could have been drawn. So I always start by drawing the angle that I know. I don't know how long this side is going to be, and I don't know how long that side is going to be, but I do know that the angle here is going to be 45 degrees. And this is angle A, so I know side A is actually going to be over here, okay? So let's just call this side B. Let's say it's, nope, false. We're going to call this side B equals 8 centimeters. And it turns out that, if I've done my drawing okay, which I probably haven't, there's actually 2 options for side A. Side A could be 5 centimeters going this way, or could be 5 centimeters going this way. 2 different possible triangles that satisfy the qualities of having a 5 centimeter, an 8 centimeter, and a 45 degree angle. So a definition for ambiguous case, the ambiguous case, this is a problem that has 2 or more solutions. A problem that has 2 or more solutions. We're going to run into that in this lesson, and you're going to have to choose the correct answer or come up with both answers. What else do you have? We have a little reminder of 2 laws that we use a lot in trigonometry. We have the sine law. Does anyone remember what that is? The sine of angle A over the length of side A. That ratio is equal to the sine of angle B over the length of side B, its opposite side, is equal to the sine of angle C over the side length C. Okay, this is one way to write it, but what's true, if these are true, then their reciprocal ratios are also true. So if you're looking for a side length using the sine law, you would put your unknown variable in the numerator, in which case you would have A over sine A is equal to B over sine B is equal to C over sine C. And in order to use this, you need to use two of the ratios to make a proportion. So a proportion is when you set a ratio equal to another ratio. So in order to use this, you need just you need opposite information. So you need angle A and side A, and then you need one other piece of information from these 2 ratios in order to solve for the unknown value or the missing value. If you can create one of these ratios, you can usually use the sine law. Okay, so you need opposite information, we always say, an angle and its opposite side, or a side and its opposite angle, to make the sine law usable. The other thing that we have, which is going to come up in today's lesson, is the beloved cosine law.
Is there a definition?
Nope, this is the sine law. This is just something that is always true in acute angle triangles. Cosine law. And the cosine law, that's a little bit harder to remember probably, but it says that a squared equals b squared plus c squared minus 2bc times the cosine of angle A. All right, so this, written in this form, it's very useful for solving for a side length. If you have an unknown side length, but you know the other two side lengths and you know the angle opposite the side length that you're looking for, that's key, then you can just plug your values in here and you can figure it out. Now, we can also rearrange this in a way that's more helpful when you're solving for an angle. Okay, when you're solving for an angle, if you're solving for angle A, the relationship between angle A and the rest of it is that the cosine of A is, and this is going to have a numerator and denominator, b squared plus c squared minus a squared over 2bc. I'm not going to show how this equation comes from this equation, but they're literally the exact same equations, okay? Just rearranged in terms of the angle solving for, and here you're solving for a side length. One other thing I'll just say is that you don't have to be solving for angle A. You could be solving for angle B, in which case you'd have a squared plus c squared minus b squared over 2ac. Whichever letter, capital letter, is here, okay? The other two lower cases are here and here, and its lowercase, its matching side length is the one that gets subtracted at the end. That's how you can remember. Same thing is true here. I could rewrite this in terms of solving for the, maybe b is my missing side length. Then I would have a squared plus c squared minus 2 times a times c times the cosine of a, okay? And notice this multiplication symbol, I'm only putting it in there so that you can see that it's multiplied, but that it doesn't get confused with the c here. So it's 2 times a times c times the cosine of a. This is all a big multiplication thing that happens all at once. And then you can do this and subtract this from that. Then take the square root of both sides and you'd get the missing side length. Okay, that was too long. Let's get into some examples.
How can you have?
Remember, lowercase letters are always side lengths. Capital letters are always angles. Same thing here. Capital letters are angles. You can take the sine of an angle. You can't take the sine of a side. It doesn't make any sense. The sine of an angle is a relationship of side lengths, but you take the sine of the angle, and here you have lowercase letters on the top. Those are the side lengths that are opposite the corresponding angles. In example 1, we are using, again, this lesson is going to be all about using the tools that are in our toolbox. So we have primary trig ratios, SOHCAHTOA. We have Pythagorean theorem, a squared plus b squared equals c squared. We have the sum of interior angles in a triangle, a plus b plus c is 180. Now you have sine law and cosine law as well. Okay, so we're going to use those tools that we have in order to solve some triangles and some problems. So we have a gentleman here, Basarudin. He needs a new rope for his flagpole, but he's unsure what length of rope he should get. He measures the distance away from the base of the pole of the flagpole, 10 meters. And from this point, the angle of elevation is 42 degrees. So he looks up from there, and it's 42 degrees up to the top of the flagpole. And he needs to find out, therefore, the height of the pole, and then talk about how much rope he should buy. Okay, so we are looking for this side length. Okay, we are given a side length and an angle. Now, anytime I'm in a right angle triangle, and I have two pieces of information, and I'm trying to find the third piece of information, which tool am I using?
Primary trigonometry ratio.
Yeah.
Ratio.
And what's the little saying to help me remember what those relationships are?
SOHCAHTOA.
All right, write down the tool that you're using. And let's go for it. All I need to do is find the height here. Okay, I'm going to call it h, but I'm also going to remember that it's not the, what's the other word in the triangle that starts with an h? Hypotenuse. Okay, that would be this one right here. Okay, so I'm actually looking from angle 42. I am looking for the opposite side length, and I am given the adjacent side length. So I'm over here in tan land. The tangent of any angle is op over adjacent, which tells me that the tangent of 42 degrees is h over 10. How do I solve for h?
Forget. Oh, sorry. Never mind.
How do we solve for h? Right now I have h divided by 10.
Times it.
Multiply both sides by 10. Okay, your calculator is really good at this. You can, on this side it's easy. Boom, just left with h. And on the other side, 10 tan 42, enter. Go for it.
Nine. Let's go.
All right, so
In my head.
the height of the flagpole is about 9 meters. Okay, that's the use of one of the tools in your toolbox, primary trig ratios, SOHCAHTOA. Maybe at the end of the lesson we'll make a list of all the tools that you have.
That would be very helpful. Can you just like type them on a word now?
Okay, solve an oblique triangle problem. So here we are. Oh, we should talk about the second part. Part B on that, we were going to tell Basarudin how much rope he should buy. Do you guys know how a flagpole works?
Yeah.
So if our flagpole is 9 meters, is 9 meters of rope going to do it?
No.
No, he actually needs
18.
the rope to double back and probably, you know, some extra hanging out here that you wrap around.
18.
At any rate, he should buy maybe 19 meters. 19 meters should be good. B. All right, example 2, we're solving an oblique triangle problem. What does an oblique triangle mean? Just means there's no right angles. No right angles. Okay, so we have Patina, Quentin, and Romeo. They are standing on a soccer field. Quentin is 23 meters from Romeo. And from Quentin's point of view, the others are separated by an angle of 72. So again, if they give us an angle to work with, we want to use that angle right away. Okay, so I'm going to do my best to draw like a 72, maybe like this.
It's quite ambiguous.
72-degree angle for Quentin. It says that Quentin is 23 meters from Romeo. So why don't we just call this 23 meters. We'll put Romeo right there. And then we have Patina would be here. And from her point of view, the others are separated by an angle of 55 degrees. So she's probably not actually that far up. She's probably more like right there. Even that, she's probably actually a bit lower. Again, your diagrams don't have to be perfect. Diagrams are fairly meaningless except for the values, the numbers that you put in them. They need to be accurate, okay? But here we go. We have a triangle. We have a 72-degree angle and a 55-degree angle. And in A, we sketch a diagram. So we did that. What type of triangle is formed? It's an oblique triangle. What does that mean?
No right angles.
No right angles. There's A done. B. Is it necessary to consider the ambiguous case here? Remember earlier, if we had an angle, like if we just had the 72-degree angle, we could have actually built maybe two different types of triangles here. In this case, they've given us two angles, so there is no ambiguous case. There's only one possible solution, one possible triangle that fits this criteria. So no, we do not need to consider the ambiguous case because two angles are given. No need to consider the ambiguous case.
You use the ambiguous case when you have a length and one angle.
Yeah, you can do it with two lengths and an angle. I'll explain it. No need to consider the ambiguous case because two angles are given. We consider the ambiguous case when two sides and one opposite angle are given. When two sides and one opposite angle are given. I'm going to pause briefly. And determine the distance from Patina to Romeo to the nearest tenth of a meter. If there are two answers, which we decided there are not, then we would need to find both of them. Now, in this situation, which law can we use? Can we use the primary trig ratios? By the way, we're trying to figure out this right here. Okay? Let's call it side length x. It would really be called, do you know what the side length would be called?
PR.
Yeah, PR or lowercase q. It's opposite angle q. Good. Either way works. You can definitely use both. Okay. What tools? We can't use primary trig ratios because we're not in a. Can't use SOHCAHTOA because we're not in a right angle triangle. So I'm left with either sine law or cosine law. What do I need to check for in order to use sine law? Because I want to try that first. Sine law is easier to use than cosine law. Look, I have angle P and side length P. I have opposite information. So I can use sine law because I can complete one of the ratios. So I'm going to set up the ratio. I'm going to use sine law. And I'm looking for side length Q. So I'm going to put my lowercase letters on top. And my sine law tells me that side length Q over sine Q is equal to the length of P, lowercase p, over the sine of angle P. And from here, I just sub in what I know. I'm looking for lowercase q, so I don't know that. I keep that there. The sine of capital Q, that's the sine of 72. Lowercase p, I know. It's 23 meters. And capital P, I know. So on the bottom, we have the sine of 55 degrees. Now, I'm not going to calculate. A lot of you are going to want to right away go, okay, 23 over sine of 55. I can do that. No, don't do that. Okay? What do I need to do to isolate Q?
Bed math.
Right now, it's being divided by sine of 72. Again, it's math. Don't make up your own rules. There's already rules. Okay? So just do them. So we have sine of 72 is going to get multiplied by both sides. On the left side, that's easy. It's just Q remaining. And on the right side, I don't need to rewrite anything, but I will so that you can kind of see this. This is either, in your calculator, 23 divided by sine 55, enter, times sine of 72, or 23 times sine of 72 over sine of 55. Okay? Your calculator is really good at stuff. It can just go hit 2, 3, sine, 7, 2, divided, sine, 5, 5, enter. And you'll get the length of side Q is approximately 26.7, and we're working in meters. So Romeo is about 26.7 meters away from Patina. Romeo is about 26.7 meters from Patina. All right, example 3. We have a lighthouse, and it's an ambiguous case. A lighthouse at point L is 10 kilometers from a yacht at point Y and 8 kilometers from a sailboat at point B. And from the yacht, the lighthouse and the sailboat are separated by an angle of 48 degrees. Pause it here and try and give yourself a few seconds to try and draw these triangles. Try to draw a diagram for the situation that we can work with. Okay, in order to find the other possible distance, the other possible location of sailboat, we need a property of triangles here and of lines with a transversal. Turns out that if, so here's how we would describe it. What type of triangle did we form in this ambiguous triangle?
Oblique.
Right here, we have an isosceles triangle. Okay, so if this we knew was 8 kilometers and 8 kilometers, what's true about this angle and this angle?
Equal.
They're
also
equal. Okay, well, we found this angle. Okay, we said this angle was 68 degrees, right? So that actually tells us this angle. How?
Oh, it's 180 because it's a perfectly straight line.
Yeah.
So B1 here is this X that I have. So in our triangle here, I'm looking, right? Okay, that is actually 180 degrees minus B2 because we're in an isosceles triangle here with the ambiguous case. Well, we found out the angle of B2 is right here. This is 68 degrees. That tells us that our other possible interior angle of this smaller triangle is 180 minus 68,
Minus 68.
which is 112 degrees.
Oh.
Okay, so this angle right here, or this angle right here, is 112 degrees. Okay, now, do we have enough information to get the length of this side?
Yeah, because we have an opposite. We have a 10 and 112.
So we have 10 and 112, but we already had an opposite there.
We should use 8 and 48.
We're going to use 8 and 48 again, but look what we're still missing.
No.
The other
Okay.
angle.
But we have 2 angles, so that's not that hard to get, is it?
You just subtract.
Angle L then, the lighthouse in this triangle, ends up being 180 minus the sum of 112 and 48. That's going to get us the third angle inside our triangle. It's 20 degrees. Okay, now we can use sine law again to get our second possible distance from the yacht to the sailboat. Here we go. We're looking for side length L in our skinnier triangle.
Where would angle L be on a...
This is angle L.
Yeah.
All right. We have L over the sine of L, which is 112. So the sine of 112 degrees is equal to 8 over the sine of 48. Multiply both sides by the sine of 112. And we end up with a length of approximately 3.7 kilometers. So, 2 possible solutions. Either the yacht and sailboat are 9.7 kilometers apart, or 3.7 kilometers apart. The information that we have is not enough to determine what situation we're in. Ambiguous case.
Find the average.
Example 4, we are told that we're going to end up using the cosine law. So the radar screen in the air traffic control tower shows a Piper Cherokee 15 kilometers from the tower at a direction of 30 degrees east of north. So if we're drawing, here's north, here's our tower, and we're looking at 30 degrees east of north. So out here, .30 east of north is this angle, and it's 15 kilometers away. So let's put our Cherokee here, and we know that's 15 km. see what else we're working with. There is also a Cessna Skyhawk 16 kilometers from the tower in a direction of 40 degrees east of north. So now we have 40 degrees east of north, 16 kilometers. I don't want to put it there, that's confusing. I want to put it right here-ish. I'll just erase that 15, I'll put it back later. Okay, that's 40 degree angle. This is 15 km. And that was the Skyhawk S. What do we need to figure out? This is the closest that they get to each other, the Cherokee and the Skyhawk. If the two aircraft are less than 2 kilometers apart, the controller must file a report. So we are trying to figure out this distance. We want to find out if the control tower needs to file a report. Okay? So a couple of things that are involved here. We're looking for this triangle, information from TCS. What information do we already have from TCS?
We can find out the angle.
40 degree.
That's 10.
Oh.
Okay, so we can find out this angle. We can find out angle T. Okay, how are we going to do that?
Just subtract. Let's subtract 40 and 30.
Yeah, so from the tower, comma, the aircraft are 40 minus 30 equals 10 degrees apart. Okay, so we've got this angle, it's 10 degrees. What else do we have from that triangle already? Pardon? Yeah, we have 2 of the side lengths. Now let's look at the side lengths that we have. We don't have any opposite information. Okay, we don't have any angles and opposite sides together, but we do have 2 sides and their contained angle. Okay, so we have side, angle, side. I'm going to write that in words. 2 sides and their contained angle. Okay, hopefully that's fairly familiar to you. Basically all we're saying is that in any triangle, if you have side, angle, side right in a row, okay, 2 sides and their contained angle, what are you going to use? Use cosine law. Use cosine law. All right, let's go ahead and solve this. It's not necessary to solve the ambiguous case, okay, because we have side, angle, side, not side, side, angle. Side, side, angle, you would require ambiguous case. So let's determine the actual distance here. And because we are looking for a length here, and I'm going to call it D for distance between the two, okay? So I'm going to introduce that. I'm going to say let D be the distance between the aircraft. And we're using cosine law, and I'm solving for a length. So I'm going to use cosine law that leaves a length squared on the left side.
Oh, that big long.
And then I simply have my other 2 side lengths, the sum of the squares of those side lengths. So 16 squared plus 15 squared, or the other way around, doesn't matter. And then I need to remember I'm doing 2 times 15 times 16 times the cosine of, in this case it's the cosine of the opposite angle, which is 10. Okay, the cosine of the angle at the tower between C and S is 10 degrees, so the cosine of 10 degrees. Okay, I didn't show the standard form. Well, it is the standard form. I didn't show it with the letters. I'm just putting the values in there right away. Hopefully you can do that too. Now this you can do in a couple of different parts. Or your calculator can do this all at once. You could literally type 1 5 squared plus 1 6 squared minus 2 times 15 times 16 times the cosine of 10. Your calculator can do it all at once. You'll get that d squared is approximately 8.3. Are we done?
No, you have to.
Square root both sides. D is approximately 2.9 kilometers. Do we have to file a report?
Nope.
Nope. We do not have to file a report. Yay.
We did cosine and sine law last year, right? I kind of remember that.
This is review, isn't it?
All right, I'm going to give you the rules that should be in your toolbox, the tools in your toolbox, and then I'll give you the practice problems. Maybe I'll give you the practice problems first. Page 254, numbers 1 through 8. Stay tuned for rules that you know. Okay, any triangle, what's an easy rule? The sum of interior angles. So rule number 1, if you're looking for angles and you already have 2 of them, it's really easy. Sum of interior angles is 180 degrees. Okay? What does that mean? It means angle A plus angle B plus angle C is 180 degrees. Does not matter what kind of triangle you are in, that is always going to be true. This is your trigonometry toolbox. Okay. Second thing, there's 2 things now that you can do in a right angle triangle. One of them deals with side lengths only. Pythagorean theorem or Pythagoras theorem. It states that a squared plus b squared equals c squared. I'm using all lowercase letters because we're dealing with side length. That means in a right angle triangle, I'll say that after, that they're in a right angle only. The 2 legs, the sum of the squares of the 2 legs is equal to the square of the hypotenuse. Okay? You can rewrite this a different way. If you knew the hypotenuse, you could take the hypotenuse squared and subtract either of these legs, so a squared, and that would equal b squared. So always remember you're doing this part first, then at the end you're taking the square root of something. Okay, good. Third tool in your toolbox. Primary trig ratios. This is SOHCAHTOA, which tells us that the sine of angle theta is equal to the ratio of the length of the opposite side over the length of the hypotenuse side. I don't need to write all of them, do I?
No.
The next one's the same. Cosine of theta is adjacent over hypotenuse. Tangent of theta is equal to the ratio of opposite over adjacent, okay? Make sure that you're understanding that you're not taking sine times some number. No, you can sine a number. In your calculator, sine is a function that will equate the ratio, the appropriate trigonometric ratio, if that makes any sense to you. Okay, these 2 are used on what?
Right angle triangle.
Only right triangles. Your next tool that you're going to look for, if those don't work or you're not in a right triangle, the first tool you're going to try to use at that point, unless you're using the sum of interior angles, because that would be easy, you're going to be looking for sine law. Okay, sine law, we already wrote 2 different ways at the beginning of this lesson. But basically, sine A over A, right, over A is equal to sine B over B is equal to sine capital C over lowercase c. And you can rewrite this flipped over. Okay, when do you use this? When you have opposite information. Use when you have opposite info. Okay, that's just a way of saying you need an angle and its opposite side in order to use it. And if you can't use sine law because you don't have opposite information, chances are you're going to be using cosine law. And you use this when you have side angle side, or two sides and their contained angle. There are two different ways to write it. I'm going to use funny letters. I'm going to use p squared equals q squared plus r squared minus 2qr cosine of capital Q. You could rewrite that in terms of an angle. Okay, that could be the cosine of Q is equal to, I wrote it wrong. It's supposed to be capital P over here. The cosine of P is equal to Q squared plus R squared minus lowercase p squared all over 2qr.
But that's only if you find the numbers.
Use when given side angle side. The last thing that you might want to remember that I'm not putting in your toolbox is ambiguous case. So if you're given side angle, then there's two possible solutions.
You have like a little triangle that shows what that.
What about secondary trig
So
ratio?
here you're looking at any triangle, ABC adds up to 180. Here you're looking at right angle triangles, where C is always the hypotenuse. Okay. Here you're looking at right angle triangles, and it's relating each angle, the acute angles, to the side length, a ratio of certain side lengths. So if we're just looking from angle A, then we have op and adjacent, and the hypotenuse is always the long one. Okay, if you were looking from this angle, then you'd have opposite and adjacent. Sine law is in any triangle. If you have, let's say, A and side length A, and you have angle B, but you're looking for side B, okay? Then that's when you would use that looking, that would be this one upside down. So B over sine B equals A over sine A. Or if you have opposite information and you're looking and you have the side and you're looking for the angle, okay? Anytime you already have opposite information, that's when you're going to look to use sine law. Cosine law, little diagram for when you would use that. I got space here. 1, 2, 3. If you have this side and their contained angle, then you can find really anything else in the triangle. First you could find this guy. Okay, that means you can find this one. And once you have that, then you have opposite information. So then you can use sine law to find this one and this one. Okay? But the key is just this first part. If you have side angle side, and that could be anywhere. It could be side angle side or side angle side. If you have side angle side, you can find this opposite, the side opposite to the angle, the side opposite to the contained angle, we'd call it. And then from there, you can use sine law to get the other parts of it. Okay, so quite often in a multi-step problem, you'll start with cosine law. Once you have cosine to find one missing piece, then you'll be able to move to sine law because you'll have opposite information. And then generally speaking, if you're looking for angles, you'll have two angles at that point, which means you can use this to find your third angle.
What about secondary trig ratios?
Secondary trig ratios, if you run into those in word problems, you're just going to convert them to primary trig ratios. They're not super useful in solving problems.
But what about what we learned?
Okay, here's the 5 tools in your toolbox for solving triangles. Use them
And they don't
or they'll go rusty.